Okay, so this is our first example of a two-variable simultaneous, and will be the only example that I will provide in this form. We will get to situations where we need to apply it contextually, and at that point I'll speed through the context, and, well, not speed through the context, I'll speed through the simultaneous, but the context I'll spend a little bit more time on. So this is our first example. We have to solve the pair 5x take away 2y is equal to 7 and 3x plus y is equal to 8. Now, the aim of the game for the elimination method is we can either have two things. First thing we need to note is we need to match a number in the variable. So what I mean by that is we need to have the same amount of x's in both equations, or equivalently, the same number of y's in both equations. Now, the way we can do that is we're free to multiply either top or bottom equation, or indeed both, by a number. Okay, and that doesn't actually change the value of our solutions if we multiply through everything by a constant. So that's what I'm going to do. In terms of the signage, the way to remember this is if the two variables have the same sign, the two equations get subtracted from one another. So just think like a snake, S, so same sign, subtract. And if they have a different sign, then you add. Not really sure of one for DSA, if anyone has a valid acronym or a decent acronym, not algorithm, please leave it in the comments. Okay. So what I also like to do is denote equations by a name. So what I'll do is I'll note the first equation as 1 with a little circle around it. And the second equation is 3x plus y is equal to 8. Now, probably the easiest thing to do is to eliminate the y dependence, because there's a plus y, which is easy to work with and manipulate, as well as a 2y, which is fairly close to it. So the way I tend to notate this is I want the bottom equation to be doubled, because I ideally want a 2y there. So we want a 2y. And that happens when we multiply the second equation by 2. So the way I'll write this is 2 times equation 2. And I'm going to put it underneath equation 1, which remains unchanged. I haven't actually done anything to it. What we need to figure out, though, is the stuff in the second equation when we multiply it by 2. This is relatively straightforward. I'm going to take the 3x and times it by 2 to give us a 6x. Plus 2y is going to be 8 times 2, which is 16. So at this point, because we have different signs, we're going to add the two of them. Now, I do remember this one actually didn't give me a fairly nice output. What we end up getting is 11x is equal to 7 plus 16 is 23. So x is 23 over 11. And now we just need to put that into one of the other equations. Now, this one's actually not too bad to do. The easiest one to do it in is the one with the lowest coefficient of the variable you found, in this case, equation 2. So if we take equation 2 and rearrange it for y, we get 8 take away 3x, which is 8 take away 3 lots of 23 over 11. Minus 3 lots of 23 over 11 gives us 19 over 11. So if we want that as a point, considering we're talking about x's and y's in this case, the solution is 23 over 11, 19 over 11. Now you can have, relatively annoying looking solutions, but that's entirely okay. So solutions like that, not necessarily all the time, but rather often come up, and you get some really funky solutions.